Thank you, Lars, for the introduction, and welcome everybody. So as the subtitle of my thesis shows, there's an Arctic context. And the reason why I have this Arctic context is because there, in the Arctic region, so within the Arctic Circle, there's about 10% of the world oil production currently. On top of that, there is about 13% of the total amount of undiscovered oil present as well in the Arctic. And because the Arctic climate is changing, or climate is changing everywhere, but particularly in the Arctic, it becomes more accessible. So therefore, the interest increases in getting oil out of the Arctic. And with all this increased interest, there's also an increased risk of getting oil spills on water. And these are events that are very harmful for the environment and can cost millions to billions of dollars to clean up that damage. Unfortunately, the spill response methods that are currently available are not that great and efficient. For example, during the oil spill in the Gulf of Mexico from the Deepwater Horizon rig, all three main oil spill response methods that we have currently available were used, being mechanical recovery, dispersants, and in-situ burning. And these three managed to only remove 24% of the total spilled oil from the water surface. So there's clearly a gap between how much is spilled and how much we can clean up. When looking at an Arctic context and a potential oil spill in the Arctic, then the two most conventional oil spill response methods cannot really be used. They're deemed to be less suitable. So that leaves us with just in-situ burning. Why in-situ burning? Because when you burn oil, even in ice-infested waters, what is involved in the burn can be removed with a very high efficiency of 90 to 99%. It has relatively simple logistics compared to the other two response spill methods. So even though there's ice presence on the water, you can still use this method. And finally, the ice may in fact help you during this response because it inhibits spreading of the oil over the water surface, so it stays more concise and it's easier to get the fire to spread out over the full oil surface. So to give you an example of what in-situ burning looks like as an oil spill response method, this is an oil spill that we did during one of our experiments, and it has just been ignited, and the flames start to spread, and then as it came into the corner, there it stayed due to wind. And well, you can hear the sound. I did not know I had sound. The response method is about removing the oil from the water surface. So you transfer the liquid oil on the water to the gaseous combustion products and soot. And then you end up with the extinction phase of the fire, and that is one in-situ burn. And what we see after the burning, that there is still quite a substantial amount of oil left on the water surface. And this is where the burning efficiency comes in, because not all of the oil that was involved in the fire is actually removed from the water surface. And this is where the knowledge gap comes in, because we don't really understand currently what is it that determines how much of the oil gets burned during a fire. And considering we need high burning efficiencies, because then we remove most of the oil, it's quite essential that we can predict whether or not a burn will be having a high efficiency. Looking at literature reports and experimental data that is out in literature, there's a lot of variation in the burning efficiencies that have been obtained. And when you plot that as a function of the oil amount, which is relatively equal to the diameter of the fire, we see that there is somewhat of a trend that the burning efficiency increases with the diameter, but there's a lot of scatter and we don't really know why or what is going on. There's no correlation between these data points. The experimental environmental conditions under which all these studies have been conducted are very different, so it's very difficult to compare this data and say, yes, the diameter is what causes higher burning efficiencies. So basically what it comes down to is that there is a lack of theoretical understanding of the fire science behind in-situ burning of crude oil on water. So that leads us to my research objective of my PhD study, and that was to improve the forecasting of the burning efficiency of in-situ burning. So we want to know how much gets burned when we do a specific burn. And I tried to study this by looking at a number of operational parameters on the residue formation from in-situ burning. And the ones shown here are all the ones that I have addressed during my thesis, but during this presentation I will focus only on 3 of them. First being the vaporization order of the crude oil and the residue that's left behind. Second, the water cooling and the effects of water below this oil. And finally, the effects of the ice and how herders can be used in ice-infested waters. So basically, oil, water, and ice. So the first research topic is the vaporization order. And what does this mean? The vaporization order determines the order in which all the components in a crude oil vaporize and therefore get burned. Crude oils are extremely complex mixtures of thousands of different hydrocarbons, and they need to interact in some way during the fire, but we don't know how. And for example, when we look at how crude oils burn and pure oils consisting of only one hydrocarbon, there's a very distinct difference between the two. On the left you have a pure oil, and on the right you have a crude oil burning. And looking at the flame height, we see that for the crude oil, the flame height clearly decreases as a function of time, whereas the pure oil remains relatively constant. To be able to explain this effect, we need to look at what do these components in a crude oil do. But crude oils are so complex that you cannot analyze all the components in a crude oil and say, oh, it consists of this and that behaves like this because of whatever reason. So instead, we look at only the general hydrocarbon properties that we can use to somehow categorize how crude oils behave. And we use hydrocarbons that are in the oil because their molecular weight basically says something about their physical properties. The larger a molecule, the more carbon and hydrogen in that molecule, certain things change. For example, the density increases, the boiling point increases, as is shown on this plot here, for the alkanes. The viscosity increases and the volatility decreases. So how easily the vapors evaporate from a liquid. To give an impression of the crude oil chemistry, this is a gas chromatogram of a crude oil, and the annotations show the different alkanes in this crude oil. And each peak you see here, even the very small ones, are at least one unique component. And especially in the lower regions, there's a lot of overlap, so there may be multiple components per peak. The important part here is looking at the trend we see in this graph, which is that we see with retention time, C8 goes all the way down to C35. So we see that the retention time basically is an indication of the molecular weight and therefore the boiling point and the volatility, which is important later on. So we don't really know how all these components behave during a fire. And therefore I looked into literature to models that state how multi-component fuels burn, so fuels with several components in them, and I found actually conflicting theories for that. So out of all the literature models, I distilled 2 for this presentation to be presented. They were the most distinctly different. The first one is the equilibrium flash vaporization. This model says that you have a constant rate and constant vaporization order as the oil burns, which means that when you put this oil on fire with all its components, they basically add up to an average amount of, or an average composition of the gases that evaporates from the crude oil. And it's continuously that average. In addition, that average is exactly the same composition as the original fuel. So you're basically burning it like a pure fuel as if it's only one component, but then you just take an average of everything. The second model is the diffusion limited vaporization, which states that the components evaporate in order of decreasing volatility. So you first evaporate the light components with low boiling points and high volatility, and once these get depleted from your crude oil, you move on to heavier components. What I did with these models is say, okay, if I have a fuel that would burn according to either of these models, how would the burning parameters behave? How would that fire behave when burning that fuel? So I made some predictions based on these models. For the equilibrium flash vaporization, what we would expect is basically constant burning parameters. We expect a constant surface temperature because the gases that evaporate are always the same. So the average of that gives the average surface temperature. And then the burning rate and flame height should also be this, constant, because the gases evaporate with a constant evaporation rate. When we would look at the residue of the oil that is left on the water after we burn it, we would see an unchanged residue composition, because what is being evaporated has exactly the same composition as what is left in the oil, or was initially in the oil, so there's no change in the chemical composition of this oil. Looking now at the DLV model, we would expect an increase in surface temperature, because you burn first the light components, which have a low boiling point. Those get depleted, your oil starts heating up, and starts to burn heavier components with a higher boiling point. And this goes on until the heaviest components are burned, ideally. So continuously increasing surface temperature. At the same time, we expect decreasing burning rate and flame height, which I have derived in my thesis, but will not go into detail here. And for higher hydrocarbon weight, you would expect these to decrease over time then. When looking at the residue composition, we expect to see a different type of residue compared to the original fuel oil, because you basically first remove all the light components, so your residue consists of only heavy components, and therefore there's a difference between what was the fresh oil and the residue. To study this, I used the crude oil flammability apparatus, which is a water tank with a 1 × 1 square meter water surface, and in that we place a Pyrex cylinder in which we contain the oil, and use amount of thermocouples to measure the temperature at different heights throughout the oil and the water layer. And this setup was used to measure the surface temperature and monitor that as a function of the burning time, the flame height using a camera to record it, and the residue composition by sampling the residue after the fire. The burning rate was measured by putting this Pyrex cylinder into a bucket filled with water and putting that on a scale, so we could measure how much oil is being lost as a function of time. So, on to the first part of the experimental results. I tested this for a number of pure oils, which by definition should follow the equilibrium flash vaporization model. So they give a nice baseline to which we can compare crude oils and see how they behave. I also made a mixture of these 3 hydrocarbons to create my own multi-component fuel and see, can I use that to simulate crude oils, because I know exactly what's in there. So if I can use it to simulate crude oils, I can study that instead and be more aware of what is going on. So I'll first show the results for the pure fuels that you see here. We see very clear constant surface temperatures on the top left graph, close to their boiling point. So that also shows that the way we get this data is rather accurate. The burning rate and flame height also stay relatively constant. Compared to the alkane mixture and the crude oils, there's a clear difference. The crude oils and the alkane mixture have an increasing surface temperature as a function of the burning time. And the crude oils clearly have a decreasing burning rate and flame height as a function of time. The alkyne mixture, however, does not really decrease so much for the burning rate and flame height, and is more aligned with the pure oils, as you can see here. The purple line, if you look at it closely, follows more the pure oils than the crude oils. Then the final step being the residue. This is the residue of one of the crude oils, this is the fresh composition of the crude oil. And when we change that to the residue, there is a very clear decrease in light components, and the heavier components that are having a higher retention time have increased in concentration. You can see that here again, how these two compare. There's a very clear difference between fresh and residue. So when we compare now these results to the model's predictions I made earlier, we see that the alkane results indeed match well with the equilibrium flash vaporization model. They show constant burning parameters, which was what was predicted. Then looking at the alkane mixture results, we get an increasing surface temperature, which matches with the DLV model, but then semi-constant burning rate and flame height, which is more in the range of the equilibrium flash vaporization. So this is kind of a bit of both. Then looking at the crude oil results, this matches pretty much perfectly with the DLV model. We have an increasing surface temperature and decreasing flame height and burning rate, and we have a very clear difference in our residue composition compared to the light crude to the fresh crude oil. So to summarize these results, we see that crude oils have a volatility-controlled vaporization model. This means all the components in the crude oil burn from first the lightweight components with a low boiling point, high volatility, and it moves to the heaviest components with high boiling points and low volatility. And this is unique to crude oils. I tried simulating it with the alkane mixture, but that showed somewhat different results. And the amount of components in a crude oil and the range that these components have in physical properties is just so broad that it's not capable of being simulated with something easier that we can understand and fully characterize. So that's a very important thing. If you want to study crude oils, you need to use crude oils. The effect of this vaporization order is that if we want to reach high burning efficiencies, we also need to reach very high temperatures of that oil as it burned to evaporate the heaviest components in that oil. As you can see in this residue, it has only 50% burning efficiency, and most things in the residue have a very high boiling point. And this chromatogram does not even show the highest boiling point components. So there's even more in the crude oil that has way higher boiling points. So we know that the oil needs to heat up. But we also have a water layer below the oil, and what this water layer does is that it cools down the hot oil during the burning. When we look at the burning efficiency for small-scale experiments that I did in the COFA, then we see that the burning efficiency decreases as a function of decreasing volatility of the oils. So oils with a higher amount of heavy components have lower burning efficiencies. When we look at the graph where we plot the burning efficiency as a function of the oil amount, we see that this scatter in the small scale is somewhat present here as well. So what we see is that in small scale there's a very wide range of burning efficiencies that we can get, but in a large scale we don't really see that. So this gave the idea that somehow large scale experiments have reaching a higher temperature inside the oil slick that is capable of evaporating all these heavy components so that it reaches high burning efficiencies. So what would be the effect of the diameter? Well, that is because the pool diameter makes the burning rate increase in the range from 0.1 to 2 meters in pool diameter. And this is the most important range for in-situ burning experiments because that basically covers laboratory experiments with diameters of 16 centimeters to intermediate scale experiments with 1 to 2 meters in diameter to the full-scale operation fires where you have way over 10 meters in diameter, and those have the highest burning rates. So we know that the diameter changes something about the pool fire dynamics that has an influence on the burning. And that is because the burning rate determines how much heat is being released during a fire. And of all the heat that is being released during a fire, some of that heat is being fed back to the fuel surface. And that is used to heat up the fuel to get the temperatures you need to evaporate the highest components. But because we're burning oil on water, there's also a loss to the water. So we lose energy to the water that cools down the oil, so we do not reach those high temperatures. This equation I derived in my thesis, and the important part is highlighted in orange, which is the heat loss term. And we see that if we would increase the burning rate, the m dot double prime, that term becomes less significant. So with increasing diameter, the losses to your water become less significant. So increasing the diameter basically increases the amount of energy that is available to heat your oil slick. You add more energy, or you release more energy, therefore more energy goes to your slick, and the amount of heat you lose to your water is less significant. To test this rather theoretical derivation, or theoretical idea, we did experiments on the heat losses. Those were done in the COFA setup, where we measure the oil gradients throughout the oil and in the water to see what are the temperatures in the oil compared to the water, because that determines the heat losses. And second, we try to simulate large-scale experiments by adding additional heat to a small-scale experiment and see, can we then reach these very high boiling burning efficiencies? And I did that in a cone calorimeter setup, which is a setup that radiates external heat on your oil slick. The oil slick is in a cylindrical sample holder. This holder was hollow, so I could flow water through it to get the same type of heat losses as in the COFA, so I could compare the two experimental setups and the data between these setups. So the first data set I want to show is from the heat losses, where we see that the temperature difference between the burning oil surface and the water-oil interface increases over time. And that is because your oil heats up over time. It burns heavier components with higher boiling points. But because of the water cooling, the lower region of your oil cannot follow that temperature increase as fast, and you get an increasing gradient. And therefore, you get an increase in your heat losses. And when we then look at the burning efficiencies in our small-scale experiments, we see that the crude oils, Duc and Repco, which have increasing heat losses, also have the lowest burning efficiencies compared to the pure oils, N-octane and dodecane. So there is a rather strong correlation here that when you have higher heat losses, you will burn less of your oil. So by adding heat, should we then get a higher burning efficiency? And indeed, the results showed that with increasing the amount of heat you apply, called the incident heat flux, you increase the burning efficiency. When you do not apply any heat, you see the same amount of scatter in your data as you would expect from the decreasing volatility of these crude oils. So the ones with low volatility have lower burning efficiencies than the one with higher volatility. But as we go higher in heat flux, they converge somewhat to the same burning efficiency. So you can see on this graph that at heat flux of about 20, the burning efficiency of most of the oils starts to combine. So there's enough heat to evaporate anything from your crude oil, even the highest components, and they burn all of them, independent of what your composition of the oil is. So when we then look at this graph again with the burning efficiency as a function of the oil amount, and we have this scattering, we remove that, it becomes quite clear that there's a relationship between the burning efficiency and the pool diameter, because the scatter we see at low burning efficiencies is mainly due to a lack of heat flux, a lack of heat being transferred to the oil slick, which is a function of the diameter. So the diameter explains the scatter in this plot. However, what we were not really able to do is simulate the highest burning efficiencies of 90 to 99% in these small-scale experiments. So I tried to see if maybe the heat fluxes I used were too low, but doing an estimate of a large-scale burn, we saw that the heat flux being transferred to oil in a 10-meter diameter pool fire was only 70 kilowatts per square meter. When we go back to our experimental results then, that limits the burning efficiency to about 80%. So we know there's a function of the diameter, and that is partially due to the heat balance, but the remaining percentages that really boost it to these high 99% are currently unsure. And there's some speculation in literature on what these effects might be, but they are currently not known. And in my thesis, I have not been able to go there yet, so that's still part of ongoing investigations. The water does not only cool oil, it also heats up by itself and then can interact with the burning oil. And that is called the boil-over phenomenon. This is a video where you see the oil burning at the end of the fire. So we saw the flame height video where the flame height was going down, and this is right after that moment. So the oil has burned most of its light components. It's now very warm, and therefore, because it has high temperatures, it starts to give more temperature or more heat to the water layer, so the water starts to heat up as well. And what happens is that the water reaches its boiling point, but it cannot evaporate because it's covered by oil. It cannot go into a gas phase until the moment that it heats up to about 120, 150 degrees, and then the oil is no longer enough a barrier to prevent the water from reaching a gas phase, and it violently evaporates, throwing steam and oil droplets in the flame that cause a chain reaction that results in what you just saw, an increase in burning rate and flame height. a side effect of this is that often the flame goes out soon after boil-over is initiated, and we still see a residue on the water surface. So it's not necessarily a phenomenon that is desirable. On top of that, we don't really see this during operational scale fires on sea. So it could be that this is just an artifact of laboratory studies, because on sea you have the sea current that might cool the water below the oil so that it never reaches these 100 or higher temperatures. So when doing these scale experiments, we need to make sure that this phenomenon is either genuine or should be prevented. So we looked at this by introducing a water current in the body of the COFA. We used a low cylinder and with a propeller created a water current below the COFA. We also have the cone experiments where the oil and water was separated, so there, even though the water heats up, it will never lead to a boil-over. And we can test whether oils can go into boil-over by themselves or that it's purely related to the water. Well, what we saw clearly is that when you cool the water below an oil slick that burns, the water will not give you a boil-over. It will just burn out, the flame goes down, and instead of giving this final explosion, it will just die out. But in the cone, we did see different behavior for some of the oils. On the left, you see a typical oil that burns, and that burns as if the water has been cooled and there is no boil-over. In the middle, we have a crude oil with both a large amount of light components and a large amount of heavy components. And on the right, there is water mixed in the oil, so there we expect boil-over. So this is how that looks. We can clearly see that the grana has some sort of a boil-over phase. It's having a larger flame than the IFO 180, but not as much as, it's not as violently boiling over as the emulsion does, which will become obvious quite soon. So there's something going on with the grana that causes this boil-over, despite there being no water in it. Interestingly enough, after the boil-over of the grana is done, the flame does not extinguish. It just continues to burn. And this led us to believe that the burning of this crude oil has to do with the composition of the crude oil. When you have the water layer, you need to make sure to cool it, because otherwise you might get a boil-over due to water. But crude oils can also lead to a boil-over. And we attributed that to the light components in that crude oil being trapped in the crude oil and basically function as the water. So you have all the heavy components at the surface. The light components cannot evaporate because they're trapped. And then those start to heat to very high temperatures and give this more violent burning. So onto the sub-conclusion of the water results. We saw that the burning efficiency depends primarily on the pool diameter, and this is partially related to the heat balance. So you have heat coming in because of the flame and heat going out to the water layer. And this is unique to crude oils, that it is pool diameter dependent, because crude oils are the only type of fuel that are so dynamic and heat up as a function of time. So if your fuel would not heat up and increase the heat losses, it can burn out steadily. And there's no need to have a high diameter to mitigate these heat losses with a higher burning rate. When downscaling experiments, it's important that you at least apply this additional heat to mimic larger scale experiments. Even though it does not explain everything, it is at least a start to get to higher burning efficiencies. And you should also get a current in the water sublayer or somehow cool the water so it does not give this artificial process of a boil-over phenomenon by having a steady water layer that heats up over time. On to the final research topic, which is about the ice effects of in-situ burning of crude oil on water. And this is a bit of a jump, but in order to ignite crude oil, you need a 1 to 2 millimeter initial slick thickness. And that is because otherwise your heat that you apply to heat up the crude oil and get it to its flash point where it can ignite, you just heat up the water instead. One way to thicken oils on water is by using a chemical herder, which is shown in this video what that is. Chemical herder is a surfactant that once you apply it to the water, it starts to spread out. And it spreads out with more force than oil spreads out, so it basically pushes the oil back. If you put it around the oil slick, the crude oil will be pushed towards the center, the volume stays the same, the area decreases, so the thickness must increase. And you get a thicker oil slick. Now, normally, the conventional method to thicken oils that are spilled on water is by using booms, as you see here, the red barrier on the picture. This is being pulled by one or two boats, and as the oil stays on the water surface, the boom is getting pulled forward, so the oil stays in the back and gets thickened in the back of the boom where you can burn it. But in ice-infested waters, the ice starts to clog up the boom with more ice than oil, and also interact with the boom, and it can lift up the boom as you push it forward, and then oil starts leaking out. So it's not an ideal method, and it has been shown that you can use it up to 3/10 of ice. Herders have been shown to work in ice-infested waters and can thicken oil slicks relatively easy. But one of the problems, what I showed on this schematic, is that it can break up in multiple slicks. And we know now how important the diameter is. So if we start breaking up our oil slick in smaller ones that all have lower burning efficiencies, our response method will be less effective. So this warranted some studying. And I did that by simulating oil spills at the edge of an oil slick, as you can see in the orange box. And then I looked at the spread out thickness before adding herder and the thickness of the herded crude oil, how the oil looked after applying the herder, and whether or not we could ignite it and what then the burning efficiency was. So we first did that in small-scale experiments in the COFA setup, where we did not use a Pyrex cylinder, but now use the whole basin. And we used about 200 grams of oil in no ice, and then 3/10, 5/10, and 7/10 of ice coverages. We scaled this to intermediate scale to be able to see, do the results compare between these two scales? Because if so, we can extrapolate that to the full-scale herding operations. Due to practical reasons, we tested this only for 2.5/10 ice coverage, but we also tested a larger amount of oil to test if we scale the diameter, do we then indeed get a higher burning efficiency? So these are some of the experimental results of the small-scale experiments. And you see here snapshots right before the herder is applied, after about 30 minutes of having the oil spread on the water surface. And in each frame, the herder will be applied in the bottom right corner. And then it looks like this. The oil clearly moves through the ice. So the ice does not inhibit the herding process in itself. And we get thicknesses that were, before we applied the herder, could not be ignited. The oil could not be ignited. And after the herding, the thicknesses were about 2 to 10 millimeters, which was in an ignitable range. But we also see that with the fracturing of these oil slicks, increased by having more ice. It started to interact with the ice and break up in smaller droplets. This did not really matter for the burning efficiency, though, in these scales. Even though we had to use more ignition attempts, in this small scale that was rather easy, and we could burn about 40% in all ice coverages. Moving on to the experimental results for the intermediate scale, at the orange arrow, we see that the herder is being applied. And what you see here is that the whole basin is covered in oil. It's rather difficult to see. So the red line indicates the separation between clear water surface on the one side and oil surface on the other side. And in the last frame, everything around and darkened in black is oil. The fracturing process, so the breaking up of the oil slick and the herding process of getting the oil together, was rather similar in this scale to the small-scale experiments. So that says something that we can indeed scale these results to larger scales. Oil got trapped in between ice flows, it got stuck to ice, and as most of the herder moves forward, the main body of the oil moves as well, and as you can see between these frames, as the oil gets separated, it gets surrounded by herder and will therefore not reconnect again, so you form these separate oil slicks. In the experimental results in the intermediate scale, we did find that ignition was rather difficult. These experiments were performed outside, and especially for the small slicks that were formed, it was very difficult to get these to ignite. If you would use a torch to try and ignite them, you would, instead of getting a steady flame, push the oil away, and you start heating up water instead. So we got actually rather low burning efficiencies. The one for the ice coverages is here a little bit higher because there was more oil being packed in between ice, and that was easier to ignite because it could not spread out. So when trying to ignite, it would always have its herded slick thickness. If we managed to ignite an oil and we just looked at the amount of oil we had in that burn and see how much of that oil burned, we got actually reasonable burning efficiencies. So this is the relative burning efficiency compared to what was ignited and how much of that oil was burned, rather than how much oil do we have spilled. Maybe we can ignite 10% of that, so the burning efficiency will never be higher than 10%. But if you just look at what has been ignited, of that we burned a reasonable amount. So if we then look at how these burning efficiencies align with what has been reported in literature, is that they align actually rather well for the relative burning efficiencies, that is. So we can see that having these slicks fracture, becoming more difficult to ignite, we lower the burning efficiency. If we manage to ignite them, they're burning actually rather fine. Looking then at the results from the 12,800 gram oil experiment, we see that the burning efficiency aligns rather nicely with the diameter. And because we did these experiments under very similar conditions, this gives further support that the burning efficiency increases with increasing diameter. So to summarize these results, the chemical herding successfully facilitated in-situ burning of crude oil in ice-infested water. If you have an oil spill in ice, you can use a herder to thicken it so that it becomes ignitable. The problem is that you get the fracturing of the oil. So unless you have a mechanism to ignite all these small oil slicks or prevent the oil from breaking up, you get a lower burning efficiency. Once you manage to ignite the oil, it burned fine. We get burning efficiencies that we expect based on the size of the oil spill. So we can use this method in ice-infested waters, but there are still some practical problems that need to be solved for that. On to the final conclusion, where we combine all these three topics. What have I learned during this PhD study? Well, the first point is that crude oils are a unique type of fuel that burn from the light components to the heavier components. And therefore, in order to burn all of a crude oil, you need to continuously heat up that oil slick. And this is unique to crude oils and not mimicable by any other type of fuels. Now, the burning efficiency of a crude oil is therefore governed by the pool diameter. That is the main parameter that determines whether or not you will have a high burning efficiency. This correlation between pool diameter and burning efficiency is in part due to the heat balance, because higher pool diameters add more heat and the losses are less significant, so heating up the oil slick is easier and you can reach higher temperatures, so burn more of the oil. But it does not explain everything. There are still some parameters about the pool diameter that we do not understand why they result in such high burning efficiencies. And finally, if we want to use this oil spill response method in the Arctic, then herders are possible to be used. They can thicken oil slicks from non-ignitable thicknesses to ignitable thicknesses, but the practical issues related to ignitability of fractured oil slicks have to be solved to fully unlock the potential of in-situ burning to be an effective oil spill response method. Now, going back to the research objective, where I wanted to improve the forecasting of the burning efficiency of in-situ burning by looking at different operational parameters, I'm very confident in stating that the main parameter that determines the burning efficiency of in-situ burning of crude oil is the pool diameter. So high burning efficiencies are inherent to large-scale fires. What this means from a practical point of view and performing this oil spill response method is that the ignitability is in fact the most important parameter in determining whether or not you can use this oil spill response method in practice. Because once you get to ignite your oil, it will have a high burning efficiency as long as you burn enough oil, which you typically see for an oil spill. And with that, I would like to thank you for your time and my sponsor that funded my PhD study.